out the last sort of differentiation rule that we need to learn. That's implicit differentiation. So this is a very similar one to what I did with you in class. So if you remember, what I said is you don't need to make y the subject in order to be able to differentiate a function. Actually, this isn't a function, but you know what I mean. We are able to use a process of implicit differentiation for when y is not the subject, okay? And it just goes a little bit like this. It says, let's differentiate each component of the function with respect to x. Okay. dx of 4. Okay. It's easy to do for x squared. We can differentiate that with respect to x, no problem. That's 2x. We can differentiate 4 with respect to x. That's just 0 because it's a constant term. It's the y squared that is the problem. We cannot differentiate a y with respect to x. So what we do is we cheat. We say, I won't do that. I will differentiate it with respect to y. And I will use an application of the chain rule where I will multiply this by dy dx. The effect is that you're doing what you wanted. Okay, you're doing it, you're differentiating it with respect to x, but you're doing things you can actually do. So you end up with 2x plus, should have a plus there, 2y dy dx. So I've differentiated with respect to y and then multiplied by dy dx. And now what I can do is I can rearrange this function for dy dx, and you're going to get dy dx equals negative x over y. Okay, so there is the general rule for differentiating something that is not with respect to the variable that you're interested in. Okay, so differentiating y with respect to x. Now what I'm going to just convince you of here, well, this is actually what you've always been doing, you just perhaps didn't realise it. Because if we take a normal easy function, let's say something like y equals 3x squared plus 2x, we can differentiate this implicitly as well. In fact, we have always been differentiating it implicitly. Because what we're going to do is we're going to do d dx of each bit. Okay, just the same. Okay. Now, what we're going to do, if we differentiate y with respect to x, what we're going to need to do is we can't do that, so we're going to do dy of y and then multiply it by dy dx. And the other bits are easy. So that's going to become 6x plus 2. And what is the differential of y with respect to y? Well, of course, it's just 1. So this bit just disappears, really. And what you're left with is dy dx. So dy dx is equal to 6x plus 2. So actually, you're always doing implicit differentiation. You just perhaps don't realise that that is what you're doing. Okay? And it's only when y is not the subject of the function that it matters. Let's have a look at some more questions, okay? Let's have a look at A here, which is nice and easy. We're going x squared plus y cubed equals 8. So again, differentiate each of these bits of the function with respect to x. Okay? First bit here is easy. We're going to get 2x, because that's in x, that's fine. What we're going to do is we're going to instead differentiate with respect to y cubed, and then multiply that, use the chain rule, by dy dx. And then the next bit is easy, that just becomes 0 because it's a constant. Okay, so what do I get? I'm going to get 2x plus, differentiating y cubed with respect to y is 3y squared, and then I'm left with this multiplication of dy dx. Okay, so dy dx is going to be equal to negative 2x over 3y squared. So now it's very, very important that you understand that if you want to be able to find a gradient at a specific point, you need to know both its x value and its y value in this instance, okay? Maybe you want to find the stationary point here. Well, that's when dy dx equals 0. Well, that implies that that's when minus 2x equals 0. It's when x equals 0. So for this, we have a stationary point at x equals 0. There may be two places where that happens, okay? If it's not actually a function, it's a many-to-many mapping. So you've got to be really, really careful with that. We'll perhaps talk about that in a second, okay? Right. B is a bit trickier, okay? What we've got here is we're going to have to combine some rules. I've got x squared y plus y cubed equals 100. Right, so again, same tactic. Let's differentiate each bit with respect to x. Okay, and a lot of this now is easy. Certainly the first bit easy, that's just going to be 1. The y cubed is easy. If you've been paying attention, it will become d dy y cubed, and then use the chain rule, multiply that by dy dx, okay, and that's going to be equal to 0. Okay, so I'm going to get 1 plus 3y squared dy dx equals 0. It's just this bit that I haven't yet done. How am I going to do that? Well, what I need to use there is I need to use the product rule. Okay, what I'm going to do is I'm going to use Newtonian notation here. I think it's the easiest way to do it with this particular problem. I'm going to let u equal x squared, and I'm going to let v equal y. Then what I'm going to do is I'm going to differentiate each of these with respect to x. So I'm going to find, let's make it really clear. So this is du dx. That's easy, that's 2x. I'm going to also try to find dv dx. I can't do that. What I need to do is I need to find d dy of y times dy dx. Okay, so what I end up with here is the differential of y with respect to y is 1. So I get dv dx equals dy dx. Okay, and there are my 4 components. I'll just delete that there. I've worked out that dv dx equals dy dx in this instance. And then what I'm going to do is I'm going to apply the product rule. Well, the product rule states that I'm going to do this multiplied by this, and then add this multiplied by this. So what do I end up with? I end up with x squared dy dx plus 2xy. So this bit in green here differentiates to become this here. Okay, so I'm going to put it in. So I get plus x squared dy dx plus 2xy. Okay, now what I've got to do is rearrange this for dy dx. So I'm going to do this. I'm going to say x squared dy dx plus 3y squared dy dx is equal to negative 2xy negative 1. Then I'm going to factor out dy dx. So dy dx becomes x squared plus 3y squared Okay, and what we're going to do here is we're going to then divide both sides by x squared plus 3y squared. So dy dx is equal to minus 2xy minus 1 all over x squared plus 3y squared. So you found the gradient function in terms of x and y. So if you want to know what the gradient is at a specific point, you need to know both the x and the y value at that point. Okay, I hope that makes sense. So you need to do implicit differentiation, combining the product rule into that. Okay, you can ask me if you're not sure. So you can then start to apply all of this stuff, same sort of things that we can do with normal differentiation. So we've got x squared plus y cubed equals 5. We're asked to find the gradient of the tangent at the point where x equals 2. So let's do an implicit differentiation. Okay, what are we going to get? We're going to get 2x plus, I'm just going to skip through the rule here. Like, again, once you spot the pattern here, it becomes very, very easy. 3y squared dy dx equals 0. So dy dx equals negative 2x over 3y squared. Now what we want to know is what is the gradient of the tangent at the point where x equals 2. But I can't work this out unless I know what the y value is as well. So what I'm going to have to do is I'm going to have to say 4 plus y cubed, because I'm subbing the x equals 2 there, equals 5. So y cubed equals 1. So y equals 1. So I'm actually looking for it at the point where x equals 2 and y equals 1. So now I can sub in, let x equal 1 and y equal 2, and dy dx equals minus 2 over 12. So it equals minus a sixth. So the gradient at the point where x equals 2 is minus 1 over 6 for this function here. Okay. Here's one that involves exponentials as well. Okay, so this is very, very tricky. It's going to involve a lot of interesting stuff. Okay, what I'm going to do is I'm going to let u equal x cubed. I'm going to let v equal e to the 3y. I'm going to let a equal 4x squared, and I'm going to let b equal y cubed. Okay, because I'm going to have to use the product rule on those parts. Okay, so what do I need to know? I need to know du dx. That's easy, that's 3x squared. I'm going to need to know dv dx. That I'm going to have to do implicitly, which is going to be, so I'm differentiating with respect to y, which is going to be 3e to the 3y, and then times that by dy dx. Okay? Left myself a bit of space there. I'm going to do dA dx equals, that's easy, that's going to be 8x, and dB dx, again, do it implicitly. You're going to get 3y squared dy dx. Okay, so now I've got all the component parts that I need. So this requires the product rule, so I'm going to have to do let me do it in green so we can see what's going on. So it's going to be this times this. Okay, so it's going to be x cubed times the differential of the other one, which is 3e to the 3y dy dx, plus this times this. So it's going to be plus 3x squared times e to the 3y. That's just this bit here, okay? Let me do this in orange, so let's do this bit. That is going to be this times this. Okay, so we're going to be adding on 4x squared, it's going to be 12x squared y squared dy dx. Okay, plus this bit times this bit, so that's going to be plus 8xy cubed. And then finally, the last bit is easier. There's no product to do here. It's just going to be the chain rule. And it's in terms of x, so it's with respect to x, it's not a problem. So that's going to be minus 54 e to the negative 2x. Okay? And there we are. That is implicitly differentiated. Let me just tidy it up a bit. What do we got? See if we can do any factorization, perhaps. Don't think we're going to be able to. Well, we haven't even answered the question. I know what I'm talking about. Right. First of all, let's do some tidying up. So we're going to do x cubed, 3x cubed, e to the 3y, dy dx. Okay. Plus 12x squared y squared, dy dx equals. And I'm going to take all the other bits over, so that's going to be minus 54 e to the negative 2x plus minus 3x squared e to the power of 3y minus 8xy cubed. Okay, factor out dy dx. So that's going to be 3x cubed e to the 3y plus 12x squared y squared equals, same, e to the minus 2x minus 3x squared e to the 3y minus 8xy cubed, and then finally divide both sides. Okay, so we're going to get minus 54 e to the negative 2x minus 3x squared e to the 3y minus 8xy cubed, all divided by 3x cubed e to the 3y plus 12x squared y squared. Okay, I don't really think you can make that any more simple because there's nothing to factor out. No common factors. You can factor out something in the denominator, but it's not going to make any difference. There's nothing to factor in the numerator. Okay, so I hope that makes sense. You know, this is a nasty question, which is combining implicit differentiation, product rule, and differentiation of exponential function. Okay, which requires the chain rule. So a lot of the rules all mixed in together. Okay, it's a lot to take on board, but there we go. There's a My Maths with implicit differentiation, and I've included it in the Microsoft form as well. Okay, let me know if you need help.